Hello everyone, my name is Fabiola Pereira. I'm an MIT Portugal PhD student from Sustainable Energy Systems at the Technical University of Lisbon, Instituto Superior Técnico. And today I will present you the work that I developed about the combustion of emulsions in isolated electricity system and the reduction of pollutant emissions. You can see here in the figures some of the samples that I've produced and analyzed in this work. So we are living in the era of the energy transition. It's a new energy paradigm where the digitalization is very important and the carbonization of the electricity systems are one of the key drivers to achieve the commitment in the Paris Agreement and in the European Green Deal, and also to reduce climate change for a more prosperous and the safety of our society as well. At this point, islands are one of the particular steps in order to achieve a low carbon energy electricity system. So basically it's trying to reduce the importations and penetration of fossil fuels in the islands. And for this reason, this work, it's about a transition step that is the reduction of exhaust gases emissions from internal diesel combustion engines. So for introduction, at the first song, it has been done a literature review of the emulsion theory, according to Professor Hopkinson, and the literature review, the introduction of water in diesel emulsions or water in fuel oil emulsions have three major approaches: the direct injection in the combustion chamber, also fumigating the water into the engine take care, and in the form of emulsion. So this work, it's about the formulation of emulsions, water in fuel emulsions. So emulsions are two incubated miscible liquids. With one of the liquid is dispersed, the water phase, as a small spherical droplet in the other liquid, that is the fuel oil phase. You can see in the figures how the different steps in the combustion emulsions and how the absorption of heat performs an expansion of the micro droplets of water, and the macro explosion in the burning and oxidation step allows having a better and more homogeneous atomization in order to increase the contact area from the air and fuel mix in the chamber. And this can achieve better results regarding the coefficient of combustion and reduction of soot in the exit of the exhaust gas. So what are the advantages and the challenges of water in fuel emulsion? Water in fuel emulsions can be an economical solution because it doesn't need an engine retrofit. Also an efficient combustion regarding the better atomization in the combustion chamber, a better fuel economy as well for the reduction of fuel oil, and the decreasing temperature of the combustion leads to a drop in NOx formation in diesel engines due to an endothermic reaction of water particles in water in fuel emulsion during combustion. The addition of water has also an advantage that improves atomization, because this micro explosion of water particles improves this atomization and the mixing of air and fuel mixture, and this reduces formation of soot particles in the exit of the exhaust gases. But it has some challenges as well. It has three main challenges: trying to produce a stable emulsion in a continuous process regarding the fluctuating conditions that we have in the process, and trying to adjust these parameters regarding engine operating variables, environmental conditions that affect atomization and variability in order to have production of electricity according to the engine operation power that we have. So this introduced some challenging steps that were adjusted and during this experimental study as well. So the objective of this work is to study the combustion of emulsion to internal combustion diesel engines, including the consideration of pollutant emissions, the planification, implementation, experimental investigation of the combustion of this emulsion in a power plant, situated in Atlantic Ocean in Madeira Island, and monitoring and controlling the process parameters in order to design the reference case and then different scenarios to achieve a process model. At the same time, It was analyzed in the laboratory, the emulsion samples, according to a protocol of parameters that are defined and criteria that has to be achieved to guarantee good fitting and stability and safety of the process. A comparative analysis of exhaust gases emissions in different scenarios were created in order to design a beneficial and efficient and clean process model solution. And why? To reduce the specific fuel oil consumption, the importation of fuel oil from the mainland to the island, and also the reduction of emissions such as CO, CO2, hydrocarbons, that doesn't include methane, so high hydrocarbons, NOx and U2 and soot as well, have a better and efficient combustion and a cleaner one regarding the lifetime of these diesel engines in the power plants. So the methodology applied has been divided in three, and then there were four key steps that were always achieved and controlled. These four steps were designed originally by me for these experiments regarding safety and trying to achieve the differentiation of the scenarios to see the optimum one. So in the first place, it was designed a reference case at different engine operation system from 7.5, 8.5 to 9.5 megawatts engine power set point and only fuel oil. In the second step, it was increased the percentage of water from 13 to 50 to 80% volumetric of water in these operating systems. And then regarding all the analyses that were done in a continuous mode, it was being analyzed two process model solutions. The process model 1, 8.5 megawatts emulsion with 50% volumetric of water, and process model 2, 8.5 megawatts emulsion with 18% volumetric of water. This process goes through a batch of tests and then a continuous mode. The results shown here are the summary of results and are all related with the continuous mode of operation. So the four protocol of experiments that were done as criteria to compare these emulsions and the process model were performed regarding four different key variables: the fuel and the emulsion characterization, combustion process, exhaust gases emissions, and water. For these four process, it was analyzed different types of parameters as temperature, cinematic viscosity, laboratory analysis, droplet size, asphalt pins, the cylinder's pressure, air temperatures, and the temperature, differences in temperatures, the exhaust gases. As you can see, regarding the, it was used an instrument, the Telegram instrument, to measure the CO, NEO, NOx, pressure, temperature, and hydrocarbons without methane in the stream of the exhaust gases, and water as well, the percentage of water from 13, 15, and 80%. So results show regarding one of the criteria, that was the droplet type of emulsions. This criteria was very important in order to achieve safety and the stability of the emulsions as well. So basically, we have these two process models: emulsion with 50% of water with an average diameter of 40 micrometers, and with the 18% of water with the average diameter of 16.6 micrometers. You can see regarding the literature review that the droplet has the water that is inside, and then we can see the asphaltenes and wax of crystals and resins that are dark matter that is surrounded the water. These emulsions created were done in order to achieve less diameter of the droplets. So this step was until 16, and then we tried to achieve less one from 7 to 9 micrometers, and the percentage of asphaltene ranges from 9.4 to 6.4% of mass in order to be reductant and guarantee a better combustion and less soot particles in the exits. So regarding the four key points that were analyzed, as explained earlier, this is about the laboratory analysis of emulsion samples. So these were the parameters analyzed. It is important to understand the differences between cinematic viscosity, density, flush points, asphaltenes that were analyzed. And you can see in the figures the differences in flow in the pipelines regarding the emulsions at your left and fluid oil on your right. From Postel Model 1 and 2 and performance indicators, these were the summary of results. So you can see from Postel Model 1 that 3 systems were analyzed regarding the moisture and the creation of emulsion. From these 3 systems, S, N, and P, it was compared basically the performance of the combustion and the emissions. So you can see in process model 1 with 50% of water that the system P has better reduction of NO2 and CO emissions. And you can see from system N, results achieved show that there are better reduction in NOx and NO emissions in this system. And the system S in orange, it's in the middle. So if you go to performance indicators, exactly, you can visualize better that system P has better reductions regarding exactly these emissions, NO2 and CO. And then we have the reduction in system N that is better than in system S. We go to process model 2. There is an increase in the percentage of water. Now we have 18% of water. So the system N is better in this process because we increase the percentage of water, we reduce the temperature of the reaction, so less formulation of NOx and NO in system N, and we have, for this reason, a reduction of emissions because of the endothermic reaction. If we go for the system P, it's also achievable a reduction of NO2 and CO, but it is not at the same position as in the N. So basically the system N is better when we have introduced a higher percentage of water. But then we need to understand if this higher percentage of water will be feasible in the future. So this is the performance indicators also from model 2. You can see that we have an improvement, and on your right side we have the pressure and temperature of cylinders in the side A of the combustion engine at different set points of power, where you can see the values achieved regarding the emulsion that is completely different regarding the reference case that is fluid. So basically, trying to go have in deep vision from the exhaust gases emissions that were measured, but at 8.5 megawatts set point power with a variable percentage of water, it is possible to conclude that if we add water from 13 to 80%, the systems, all three, have a reduction of CO emissions. System P has a better reduction. If we go to NOx and NEO, we have a better and less NEOx emissions and NEO emissions in system N regarding the increase in percentage of water. About the NO2 emissions, system P achieves the lower one result for a continuous mode. If you go further, trying to understand now in a fixed percentage of water, 15% of water at different engine power set points, trying to see the percentage of charge in the engine, what is the effect regarding a stable emulsion from 15% of water in three systems that have different particularities regarding the nature of emulsions. So it is possible to conclude that it's best to operate from 7.5 to 8.5 to 9.5 megawatts set point of power, because we have been working in a percentage of charge that has less emissions. You can see that in graph number 1, where if we operate at less than 7.5 megawatts, we have some results from system S that are higher than the maximum allowed value for CO emissions. So cannot operate at this engine power set point. So it will be the best to operate between 7.5, 8.5, and 9.5. We have better results if we increase the engine charge, and because we achieve better reduction and a more efficient combustion. So you can see also that from NEO and NEOX, the system N has better results if we increase the engine power, and NEO2 has better results for the system P. So in conclusion, a comparative analysis of the potential of feeding emulsion diesel engine instead of fuel, hereby designated by system S, N, and P, was carried out in 2 process model scenarios regarding the percentage of 15% and 18% of water. The impacts of this variability in process parameters were controlled, were measured, and also defined as a process model solution and adjusted regarding the requirement to guarantee the flow in the pipeline as well, because of the kinematic viscosity of emulsion that is completely different from the fuel oil. The droplet size of emulsions was also a key criteria to be maintained, trying to reduce the droplet size from 16 to 7 to 9 micrometers. And the results indicate that system P is beneficial, and is beneficial regarding a process model scenario of 15% and 80% in CO2 emissions reduction, and also in the reduction specific for load consumption. If we go to system N, it has been beneficial and promising regarding the NOx and NEO emissions. And these results can be further analyzed for a stronger period of time. And it has also achieved a CO emission of 26.3% and total hydrocarbons without methane release into the atmosphere of about 29.5%. So the experiments and research developed contributed to a more in-depth knowledge about the potential of emulsion design of a new operating regime regarding the lifetime of the internal combustion engines that are part of an isolated electricity production system, that is the power plant situated in Madeira Island. So for the next step, it will be good to have more experiments regarding the stability of feedstock as well, and trying to see which these 2 systems could be a system that it will be in the future in the power plant. For now, we have an operation model that has 15% of water, and this achieves more reduction in CO emissions as well. So thank you very much for your attention. It was a pleasure to be here with you today. I hope if you have any questions, please just feel free to contact me for further analysis. Thank you.